You're welcome to the White Academy once again. So this morning we'll be looking at quantum mechanics. All right. So especially as related to uh, quantum chemistry generally, most applicable in chemistry. Understand? This is a field that actually both chemistry, physics, they share together. So this is very important. Now let's go. All right, now, quantum mechanics. Now, I want you to recall what's it called? Wave-particle duality. Okay? Now, when we talk about wave-particle duality, what we're saying is that there's interconvertibility between, matter, and wave. Is that okay? All right, so that this, we can go from matter to wave, we can go from wave to matter, and as a matter of fact, as far as explanation of physical phenomenon and chemical processes are concerned, okay, we cannot but just see a junction where these two actually they intersect each other. All right. Now, when you're talking about matter, talking about mass, volumes, and these are various physical parameters that you use. Okay, and then when you talk about wave, if you remember your progressive wave equation, talk about amplitude, your frequency, wavelength, and so on. Right? So you must realize this. Now, how does the concept play well, as far as chemical processes are concerned? Is that okay? Now, we're not just interested in the bulk properties of matter, as much as the nanoscale. Okay, all right. So now you understand what I'm saying as we move on. Now, let's look at it. Basically, for chemical processes, we talk about electrons. All right. Now, don't forget I'm teaching chemistry. Now, as far as atom is concerned, all these fundamental particles, remember ions, molecules, atoms, all right? And as far as chemical, process is concerned, we are so much, let me just say, convenient, with protons, neutrons, and electrons. You understand it clear? Good. So I can actually tell you that actually from beginning to the end, chemistry is all about what? Electrons. Is that okay? Which one of those particles? Of course, I cannot begin to tell you what are the properties, what are the natures, several other processes. Maybe in some other times we can talk about that. Okay? But of course, essentially is what? Is electron. All right? Okay? Whose mass is approximately 9.0, times 10 to the power minus 31, kilogram. I get my point now. Okay? Do you get what I'm saying now? So please note that. Now, electron. Now, if matter wave, interception actually is true, then we can view electron, as having both matter or particulate property. Is that okay? And then wave property at the same time. This electron we're talking about is not something actually that you can handle. Okay? You can just view it, something like a smoke that you can scoop. All right, but then one of the major things is that actually we just need to devise a model to be able to explain, what is actually happening inside matter. Okay, don't forget whatever on the bulky scale property of matter that you have. Okay, it first began with all these particulates, behavior. Take note of that. So now taking electron now. So if you have agreed with me that electron can both behave as a wave as matter, okay? And of course, we need to remember something. If you recall your classical, mechanics, all right? So that one begins, with Newton's law of motion and several other things. Is that okay? All right? That is on the properties of matter on a bulky scale. Is that okay? But as you already know that actually each of these matter are composed of all these particulates, entities that we have mentioned. Is that okay? So now there's of a necessity in order to be able to explain the bulk property of a matter. Then the best way to do that is to go back to what? Quantum mechanics. All right. Okay. So now in that view of that, now you will quickly follow with me to what we call Born interpretation. All right. So according to Max Born, you understand me? Even at this junction, let's quickly remind ourselves of a progressive wave equation so that I can understand what I'm talking about. You know, when you have a progressive wave equation, okay, let's say describing a kind of a sine curve, you understand me? So you have something like this. Are you with me now? So as the case may be, so whereby you talk about, okay, this is your amplitude, is that okay? And then between two successive threads, and this is your wavelength, which is lambda. Is that okay? And each of these represents your angular displacement. This one is 0. This one is pi over 2 in radian. Pi, 3 over 2 pi. Then you have your, 2 pi, and so on and so forth. All right? And then it follows that for your sine curve, we say that y is equal to a sine, a sine theta. Okay, all right. I recall very well that when you talk about that, what's your theta, which is your angular displacement. Okay, so let's say, okay, your angular velocity is defined as this, where this is your that's your angular displacement, in radian. All right, so that t is equal to what? Omega t. Do you recall this? Then if you put it into this equation, then you say that's what? A sine omega t. Is that right? And then you cannot but talk about what? Phase angle, and phase difference, wherever actually you have maybe two waves that are actually interfering with each other. Is that okay? So let's call that one, phi. Is that okay? So this phi, how do we come about this? So if you come around here, okay, you know that for a complete revolution, okay, that's 2 pi. Don't forget we are dealing with pi in radian. That's 360. Is that okay? So if that is the case, it means that your lambda, okay, which actually is your wavelength, that's for one complete revolution. You say that one is actually sine, that's what, to 2 pi. Is that okay? But for example, now let's say you just have maybe a particular section. Let's say, okay, from here to here, let's call it x. Is that okay? So of course, which of course is not let's call that angle, let's call it phi, okay, corresponding to x. Is that okay? So at the end of the day, so when you do those things, that, it follows that, what's it called? Your x, okay, you said that your phi, so this is phi, all right? So your phi, so it's also pi, x over lambda, if you solve that. So we call this on this a phase angle. All right, so and so on and so forth. Now what I'm bringing out is that now, so we cannot but just apply wave perspective in this. Is that okay? So if that is your amplitude, then according to Max Born, all right, now we're looking at your electron density. Okay, when you have you will agree with me very well that when you talk about orbital, you said that is a place where you can locate your electron at a particular point in time. Is that okay? So all we are just interested is where we have maximum electron density. Is that okay? So for your maximum electron density, okay, according to Max Born, we deal with probability. Okay, and then the probability of that, let's say, given a trivial wave function, let's say psi. All right. So to measure the amplitude, all right, in that direction, so that is psi, dx. If you are limited just to a particular direction, of course, it could be psi grad, okay, if you are dealing with 3 dimensions, dx, dy, the z. All right? So don't bug yourself too much with all I've just mentioned, but just to let you know that actually it is this wave concept that we apply to electron, and then from which actually we derive most of our quantum mechanical, equations or operators. Is that okay? Now, another fundamental thing you must recall, we talk about Schrodinger wave equation, all right? Or probably before we go into that now, let's quickly look at operators. Now, what do by operators? Operator actually is a mathematical rule, you know, that you apply. It's just an instruction to do one thing or the other. Is that okay? That's an operator. Okay, so we cannot but just apply all of this, you know, as far as quantum mechanics is concerned. So we have operator, you know, for velocity. I mean, yes, right. For what's it called? For kinetic energy, you know, for momentum, you know, and so on. So we see how we go about it. But then let's now, before we go in, let's quickly look at how we derive Schrodinger wave equation, because this is very important. I'm coming. Okay. Schrodinger wave equation. So now, agree with me on this. Now, I'm going to be moving from classical mechanics to quantum mechanics. Is that okay? Classical mechanics to quantum mechanics. So from classical mechanics, it follows that, let's say law of conservation of mechanical energy. You say that, okay, if ET is the total energy, all right, then it follows that EK is your kinetic energy, then plus EP, which is your what? Potential energy. Take note of that. Is that okay? So if energy is conserved, then this is true, of course, which is always true. Now, recall that your EK, all right, is equal to, what's it called? Your EK can be given as, you know, half mv squared, as you know. Is that all right? Good. And then, it's also very important for you to recall momentum. You know, we represent this as this symbol. And that's mass of what? That's product of mass and what? And velocity. Take note of that. So if that is true, then it follows that if you carry this guy now, so you substitute it into this. All right, then what do you have? So if you go on with me, or let's say if you square it, so let's just make your V the separate formula. You have your V now equals what? That's P over M. Is that taken? So anywhere you see V, just put your M right. I mean, you put this quantity right inside there. So you have this, you know, M, all right, into what do you have there? You have what's it called? You have your P over M, everything squared. Is that taken? So when that one is done, then you are left for this. The result is going to be P squared over 2M. Is that okay? This is on what? On classical, you know, mechanics or classical basis. Is that okay? As good as this is, you know, it's not good enough for us as operation as quantum mechanics is concerned, because we are dealing with what? Nanoparticles, not bulky one this time around. So as a matter of fact, so the size of what we're dealing with is 10 raised to the power minus 10 meters. Is that okay? And recall, like I've mentioned, that the size of electron, particularly, that's approximately 9.0 times 10 raised to the power minus 31 kg. You can see actually this side is so small, all right? So this is considered under quantum mechanics, not, you know, in classical mechanics. Is that okay? So things of bigger mass, higher mass can be considered under quantum mechanics. But don't forget as a basis that all of these particles make up the bulk properties or the bulk nature of whatever matter you are dealing with. So that's also very important. So in order to now, so even though momentum is P is equal to mv, you know, on classical basis, is that okay? But then when it comes to quantum mechanical, you know, analysis, so it's given as a minus, you know, I dot, you know, h hat, you know, d dx. Is that okay? So this is what we call an operator of momentum. Is that okay? So this way I'm going to carry this one now. We're going to slot it into this, and then we can play around the rest. I hope that is taken. So, and of course, this guy also can also be written in the form, you know, in the form you can write like that. But don't forget now, let's define each of this term. So this h hat here represents h over 2 pi. Is that okay? Where h is the Planck constant, 6.63 times 10 to the power minus 32 and so on. Minus 35. Then what is it called? This I that you have here actually is a complex number. All right, which is given as I, which is what the square root of minus 1. Is that okay? So we can just do some, you know, play around this. So and how do I mean? So we can have something like this guy. We can just modify this. And if you're going to do that, then what do we have? We have minus into brackets, you know, I dot squared, okay, h hat d, you know, over I, you know, dx by mathematical induction. So if you just cancel this, get this now, okay? But this guy itself, which is I dot squared, is written as minus 1. Is that all right? So therefore, what do we have? So minus times minus, that's plus, such that what we have is, you know, h hat d dx. So this is another way of writing your momentum operator. Is that okay? So whether I write in this form or write in this form, the result is the same. All right. So before I move on, or maybe let's quickly play around this. So before I now go, I know I'm deriving a Schrodinger wave equation. So recall this. This is very important. That's what we're going to slot in into this equation, and then I will continue. But can we just quickly play around something and see how this looks like and how this operates? Is that okay? So if this is true, so how do we go? Now, given a trivial wave function, psi is equal to exponential, ax. Are you with me now? So let's say that actually this is a trivial wave function where psi represents your molecular orbital. Is that okay? And it is given as this. Then and then a at is defined as your momentum operator, which is given as minus I h hat d dx. Is that okay? So then the question now is this. So then I ask that, okay, can you operate this, psi? So, and determine this. So how do you determine this? Just very simple. So all you just need to do is just to apply a momentum operator. Or you just have that as minus I h at d, dx, exponential ax. All that matters here. So therefore, once you operate or your operator, which is your momentum, to operate, on this trivial wave function, then what do you have? So it's very simple. Don't forget, given that, so this is statement. So in that sense now, so what do you remember your differential calculus? Okay, it follows that d dx, a exponential ax. You understand me clear? And of course, remember all those stuffs. Okay, let u equals to ax, so that the u, dx is equal to a. Is that right? So, and then furthermore, if that is the case, so then d exponential eu dx will still give you exponential u. If that is true, then remember our chain rule, so that d, exponential ax, dx now is equal to d du, that's the, what's it called now? So that's the d eax, du, right? Dot du dx. Is that okay? So when you play around that, then what do you have? It's just a matter of substitution. Your du dx is given as a, all right? So into brackets. Then when you expatiate this, so you got this, so you give exponential u, so that your result now is a exponential eu, and that's given as a exponential eu ax. Is that okay? So carry this guy now, slot it into this. So our result then becomes, h at, h at into, what do you have now? A, exponential aex. Is that okay? So for this is a constant now. So you have this, what's it called? So h a exponential ax. So this is your results now. Okay. So don't forget, this guy is an operator, and specifically an operator of momentum. So like I've mentioned, an operator of kinetic energy, and even Hamiltonian operator, as the case may be. You soon find out. So now for the purpose of this, so let me just quickly slot in. Let's finish this. So Schrodinger wave equation, I will come about it. Now, if you recall your operator of momentum, which is given as this, is that okay? Just put into this, and then this is what we have. All right. So if you do so, then this is what you get. So it follows that your E total, all right, as I've been giving here, is your EK plus EP. Is that okay? So now on this basis, now let V, of X, let that be what? The EP. Is that okay? So if that is okay, then what you do is this. So you go back right in here. So what do you do? Your EK has been given. So, and then we have what? I H at ddx. All right. What else? So that's okay. All right. Okay. So you have your, what's it called? Okay, that's okay. Your EK is given as this. Excuse me. So you come here. This is your operator of momentum. So don't forget this is what I'm dealing with. So fine. So that's everything squared all over 2m. So when you do so, you square this. All right. So square of this one will give you what? I dot squared. Is that okay? H at squared, d square, dx squared now dot 1 over 2m. Is that okay? So if you do so now, but recall that this guy here, is same thing as what? It's same thing as minus 1. Is that okay? So that what you then have, that's h hat square, d, square over 2m dx square. Is that okay? So this is your kinetic energy operator as far as quantum mechanics is concerned. Is that okay? Your kinetic energy operator. So you cannot carry this guy then slot into the total thing that you have right in there. So this is what you have. Okay, so you go there. So let E be your total energy, like I've said. All right, EK, in terms of the operator, we have this d square, 2m ds squared, then plus v. Is that okay? So that's what I've dealt with. Is that all right? So this is what we'll call your Schrodinger wave equation. So how do we come about this now? So all just think that now you cannot introduce your what's it called now, your psi. That is, just do this. Okay, operate this on this. Is that okay? And then let this guy also operate on this. Is that all right? So if you do so, the entire entity here can be represented as H. We call this Hamiltonian operator. So of course, where this one is what we call your observable. Is that okay? Now, one major difference between quantum mechanical treatments, is that okay, and then classical mechanics is this, Now, in quantum mechanics, okay, everything is discrete. Or let me just say energy is what? Is discrete. When I say discrete, it is discontinuous. It's not continuous. It means for every psi, okay, there's a corresponding E value.